Hi, hello. This is Prem Kumar, SM Professor, Department of Computer Science. So today we're going to see about an operating system, how the process is going to be managed. So what is meant by process management? So process management is a critical component of an operating system responsible for creating, scheduling, and determining the processes. Here's the detailed look at the key components of a process management. So we already know that. So whenever the process is being created, so it has to go for an execution, and later it has to, after completes its work, it has to go for the terminate stage. So before, what are the states we have there? So we cannot able to say that only the process will enter into the execution state, and thereafter, after completing it, it will terminate from the exit stage. Not only that, so we have some other intermediate process steps is there. So we'll see what is that one by one. So that is, so when you talk about the processes and the threads, so process is an instance of a program in execution. It includes the program code, the data, and the system resources needed to execute the program. Another one is the thread. The thread is the smallest unit of an execution within a process. So there will be a multiple threads within the same process, shared resource, but can execute independently. So which is in general we can say the smallest unit of an execution within a process is called the thread, and the process which is been executing the program which has been executing is called the process. It includes the program code, data, system resources needs to be executed in the program process category. This is the first state when we talk about the process management. Then the second one is process states. So we have several process states in this process state diagram. We have a process state diagram. It is going to depict the in clear information about the process states. So what are the states we have? It is the new state. The process is being created. Where the process is being created. The second one is the ready state. The process is loaded into the memory and it is wait to be assigned to a processor. So which was ready to get ready for an execution. So whatever the process it was ready for an execution, it will be maintained in a state called the ready state. The next state is the running state, where currently the program is going to execute. Okay, the process in currently being executed by the CPU is called the running state. Then the next one is the waiting state. The waiting state, which is nothing but either it may be we can also call as in a block state. So due to certain reasons, maybe the time slice or the IO interrupter or any other higher priority process games. So in those categories, the process will be moved from the running state to waiting stage. The process is waiting for some events to occur. Example, any IO operations or etc. Then the next one is the terminator, which is also called an exit state. After finishing the process execution, it has to be terminated from the CPU. That is, we call it as a terminated state. Next, we'll see about the process control block. The process control block is nothing but the PCB. Each process is represented by a PCB which contains the essential information about the process. See, the first one is the PCB is going to have the information about the process ID, unique identification of a process, the process state, what is the current state of the process, whether it is a running state or waiting state, or whether it is in a block state. The program counter, it will always has an address of the next instructions to be executed, and the CPU register, which is the current values of a CPU register, the current values of the CPU registers. Then the next one is the memory management information. The memory management information is nothing but the details about the processes, memory allocations, the information about the IO devices located to the processes. Okay. Then the next one is the accounting informations. So these accounting information is going to have the information about the CPU usage, time limits, and the process priorities. These are the informations we're going to have it in the process control box. The next one is the process scheduling, how the process is going to be scheduled, in what basis is going to allow the process to execution. So the OS uses a scheduling algorithm to determine which process should run at any given time. So common scheduling algorithms includes one is first in, first out. We can say it is in a first come, first serve. the process are executed in order they arrive. So if whatever the process coming first, that is going to be executed and we're going to serve it first. That we call it as in first come first serve. The next one is the shortest job next. This SJN is nothing but the process which is coming are and arriving for an execution from that which is going to use the minimum number of time, which is going to use the minimum number of time that process is going to be allowed for an execution. That is called the shortest job next. Then the next one is round robin. Here, each number of process is going to assign a quantum of time so that the cyclic order the process is being sent for an execution. That is, the processes are assigned a fixed time slicing, which is we call as a quantum time in a cyclic order. Then the next one is the priority scheduling. In the case of priority scheduling, the processes are selected based on the priority level. The processes are selected based on the priority levels, with higher priority processes being executed first. Being executed first. So whichever the process is having the higher priority, those process is going to be executed first. Then the minimum priority will be there. At last, we'll have a normal priority. So totally, we have three types of priority. The medium level of priority is called as a normal priority. By default, every process will be go under a normal priority. So otherwise, if we want to assign any priority to a process, we can give a maximum priority as well as the minimum priority. Okay. The next one is the multi-level queuing scheduling, where the processes are divided into different priority queues, and the scheduling is performed based on these queries. That is, are in the queues. The next one is the context switching. So the context switching is from the process is going to hand over from one to another state. From one state to another state, we're going to see here. When the OS switches the CPU from one process to another process, once a process enter into the CPU, and thereafter the process gets finished its work, the another process has to take over to the CPU, right? So that is from one process to another process, how the switching is going to be takes place. So when the operating system switches the CPU from one process to another, it performs a context switching. This involves saving the states of a currently running process and loading the states of a next process. The context switching is essential for multitasking but can introduce the overheads due to the time required to save and restore the states. The next one is the process creation termination. The creation of the process is going to say about a created by another process. A process is typically created by another process, that is a parent process, using system calls like fork. The fork is used to create another process. Okay, in Linux as well as Unix are the create process in Windows. When you talk about a Windows operating system, when you want to create a new process, you can go with the create process. Or in the case of Linux or Unix, you can go with a method called fork. Okay, the new process, the child process gets its own PCP. Each and every process may be a parent process or a child process. Each and every process can have its the PCP process control blocks informations and can execute currently with the parent process. The next one is the terminations. The termination is nothing but the process may determinate normally by completing its execution or abnormally due to errors. Okay, the termination is maybe after completing its work it is going to terminate, or otherwise abnormally due to certain errors, or there will be certain reasons. If any deadlocks state has occurred, there is no other option. Any other process has to be killed or terminated from the CPU, so that the resource is going to be recollected and it can be allocated to the needed processes. So that is also because an abnormally due to errors. The next one is the system calls like exits in Unix and Unix or Linux are the exit process in the case of the Windows handling of process terminations. So in Linux and Unix, we'll be using exit as a method to terminate the process, and in the case of Windows, we'll be using exit process method. Okay, when a process terminates, the operating system reclaims its resources and updates the status of the process. So after terminating a process, the process which will have hold some resources, right? So that is going to be recollected and that is going to be stored in the process state information. That is process resource states information, status of a resource. The next one is inter-process communication. In this inter-process communication is very important. How the processes often need to communicate with each other so that they can share their informations like resource sharing, message, memory sharing, and other part of the details is going to be shared between the processes. So that is what we can say it is in processes often need to communicate with each other. The IPC mechanism includes what are the mechanism it has is one is the pipes. The pipes is provides a unidirectional data channels between the processes. That is, the pipes provides a unidirectional data channels between the processes, and the other one is message queuing. The other one is message queues. That is allows a process to send and receive the message in a queue. So if anybody wants to send a message or anybody want to receive a message, only on the basis of a queue. So queue basis only the processes are allowed to send and receive the messages. The other one is shared memory. The shared memory process, what it is telling is allows the processes to access the same memory spaces. Okay, the same memory spaces is going to be occupied by or going to be shared between the one more than one process. Though those category, those processes called we can say it's in a shared memory. The other one is the semaphore. The semaphore is nothing but to provide a synchronization between the processes to avoid the conflicts. In order to avoid the conflict, you suppose if any process user A is going to read a particular file, in that case, the B or C users cannot go and access the file. So access of the file is going to be muted by the user A, so that no other can able to access it unless and until the file is been released by the process A in the user A. Once the user A releases a file access, then any other users can able to access it. That is, the mutually only one user or one process can able to access the details. The others has to wait until the resource has been releases. That is what we have to see in the case of the semaphore. The next one is the synchronization. That is, the synchronization is going to talk about when multiple processes are the threads access shared resources. When it accesses the shared resources, the synchronization is necessary to ensure the data consistency and avoid race condition. Data consistency and avoid the race condition. The techniques includes one is the mutex. The mutex is ensures mutual exclusion by allowing only one thread to access a resource at a time. That is, one process enable to access one resource at a time. So only the mutual exclusion is going to be takes place in the case of mutex. The next one is the condition variables. So in the condition variable, what it was is allows threads to wait for a certain conditions to be met, allows threads to wait for certain conditions to be met. The next one is locks. The locks is nothing but if any system gets access to particular resources, that is going to be locked until the user releases back. Okay, the prevents simultaneous access to the resources by the multiple processes or threads. This is what we see in the case of the synchronization. The next one is the deadlock prevention and avoidance. The case of deadlock prevention and avoidance, the deadlock occurs when the process are stuck in the state where each is waiting for the resources held by the other. So one process is going to access the resources which is already accessed by the another process. So this is what we call it as a state of the deadlock state. The techniques to handle the deadlock includes what are the techniques we can able to handle the deadlock situations are. One is the deadlock prevention. So what the deadlock prevention is ensures that the system never enters the deadlock state by the following certain policies. That is, example, requiring a process to request all the resources at once. So it will request at once whatever the resources it requires. All those requests is been processed. So while executing, between executing the process should not ask for any resources, additional resources. So that is can that we can able to manage only at the time of allocating a resource. And the very first time itself, whatever the resources was required by the process, it has to be allocated to the process. The next one is deadlock avoidance. What is the deadlock avoidance is the dynamic resource allocations to ensure that a system remains a safe state or an unsafe state. So when the process, it is going to have some sequence of process. So what sequence if the process is allowed for an execution so that you cannot able to get the deadlock. So that is going to be calculated and that is going to be managed with the help of the deadlock avoidance. Okay. So dynamically checks the resources allocations to ensure that the system remains in a safe state or not. So what algorithm will be using, that is the Bankers algorithm, one of the best example for best algorithm to used for avoiding the deadlock. Okay. The next one is detection and recovery. So we can able to find out whether the detect deadlock is occurred or where is there is any states of deadlock can take place. Another one is if in case any deadlock occurs, it was identified. After we identify the deadlock, we need to go for the recovering the process. So these detects deadlocks and then takes actions to recover it. For example, aborting the processes or preempting the resources. So aborting the process means will be close the process or kill the process. Our other term is preempting the resources. Whatever the resources was utilized by the process, by preempting the we are forcefully getting back the resources from the process. So that you can able to retrieve the problem of a deadlock state. So that is because of the deadlock detection and the recovery process. The next one is the process hierarchy. The process hierarchy is nothing but the process can create child processes. So it is going to create a child process, forming an hierarchy that is the parent and the children processes have a parent-child relationship, and the operating system manages this hierarchically to ensure the proper execution and the resource management. To ensure the proper execution and the resource management. When you talk about the next one, that is the process scheduling is a fundamental aspects of an operating system designs that determines how the processes are assigned to the CPU. The next one is the goals is to ensure that the system resources are utilized effectively and that process are executed in a fair and timely manner. Here's the detailed explanation of the process scheduling with examples of common algorithm. With an examples of common algorithm. So we'll see one by one what are the algorithm, how it is works. So the first one is the first come first serve. The process are executed in order they arrive in the queue, ready queue. In what order the process is arrive, those is being moved to the ready queue. It is the simplest scheduling algorithm, but can lead to the poor performance. It is the smallest scheduling algorithm, but it can lead to the poor performance. So it performs the poor performance. Why it is? Particularly in terms of average waiting time. Why? Because the first process which is coming will go and execute the other process to wait. Suppose the smallest process which was coming next to the first process. So the first process is required the waiting the execution time for the process one is 10 seconds. The other process which is coming back of the process two is maybe 1 second or 2 seconds. So the process which is going to execute by 1 second or 2 seconds, they have these process has to wait for the long time for the 10 milliseconds process has to complete. So this is depends upon the time. So that is what we are saying. It is a poor performance. That is the process waiting for an execution time is going to be extended, which is going to be long. The next one, the example for this, imagine these three processes with the following arrival time and the burst time. See the process one arrival time is 0 and the burst time is 5. So the arrival time of the P1 is 0. Sorry, arrival time of the P1 is 0 and the burst time, execution time of that is 5. And likewise, the P2 arrival time is 1 and the burst time is 3 and the P2 arrival time is 2. And so see the sequence here. At the first 0 second, you will be asking the P1 process will be at the and at the time of one, the P2 will arrive, and the time of three, the P3 is will arrive. We'll see one by one how it is being executed. The first come first serve. The first P1 starts at the at time 0 and finishes at the time 5. So it takes see so it is going to start by the 0th second and how much bus time it required? It is 5 milliseconds. So 5 milliseconds will execute. After 5 milliseconds, the 6th milliseconds, the second process is going to come over. So the P2 takes 8 milliseconds. So from 6 to 6 plus, so from the 6th location, it is going to start. So it is going to occupy 8 milliseconds over there. Okay. And when you take 8 milliseconds after that, what is the next process it was coming? P3 is going to come. So when you add after 8, when you add after 8, you will be getting the starting position of the P3 process is 16. So from there it will take totally when you add 16 plus 5, 21, 21 plus 8 will be 29. So when you add our total number of the execution time for all the process could be, will be saying that what is that 16 plus 8 plus 5, that is nothing but 21 plus 8, 29 will be the total number of time can be occupied by the process. Okay, then analysis. What the analysis was saying, the waiting time of the P1 is 0. Yes, then see this, waiting time of the P1 is 0. Then the waiting time of P2 is totally, what is the waiting time? It has to wait for until the, we cannot say it is a 5. Why? Because n minus 1 we have to take. Okay, that is, we have to say that P2 is equal to 5 minus 1. So you will be taking only 4 milliseconds for the processor. Why? Because 4 means 0, 1, 2, 3, 4. So totally will come 5. That is what we are saying, n minus 1. That is 5 minus 1. After finishing execution of the P1 process, what happens? The P2 process, then it will go to the next process for an execution. That is, the P2 will go there and the P3 will be there. So the starting time of a waiting time of the P1 could be 0, and the waiting time of the P2 is going to be P2 is going to be 4, and the waiting time of the P3 should be 6. So likewise, it is going to be wait for each process to complete its execution. The average waiting time of the process is nothing but you can able to add and divide by the number of processes. So average waiting time of each process is, that is 0 plus 4 plus 6. So will be called 10. 10 divided by 3 will be getting 3.33. This is how the process is going to be utilized. Then the next one is the shortest job first. That is the shortest job first. What is the shortest job first? Is whichever the process is arrived for an execution, from that which is going to have the shortest number, shortest time. Okay, which is the shortest time? Why we are saying about the shortest time is so that it can get completed faster when compared to the largest process, right? So that is how they see this algorithm selects a process with the shortest burst of time. It minimizes the average waiting time but can lead to the starvations. Okay, the next one is longer of the longer processes. If short process keeps happens. If any process which comes for a short utilization of memory, but the process which was already there in the memory, which was taking too much of time, what happens? The other process, whichever is coming, it has to wait. Maybe a small process or medium process or a large process. That is different. So the main disadvantage of what they are saying is the longer processes, the shorter processes keep arrival. Now see the example, the same process, zeroth entry for the zeroth time P1 enters one at the 1 millisecond. At the time of 1 millisecond, the P2 enters, and the time of P2 will be arrival at the time of 3. So total bus time for the each and everything should be 5 plus 3 plus 8 is 16. So we have already calculated. So in this significance, similarly, so at 0, at the time 0, the only the P3 is only the P1 is available. So it starts and finishes at first time. So at zero arrival, zero time, the P1 arrives. So it is go for an execution and execute. But what about the second time is, so second time it should not go for an order which was already arrived. So it is going to check whether which process completes which process is going to be executed with a minimum number of time. So see, after executing the process P1, why? Because it was initially started, it is going to occupy 5 milliseconds. Thereafter, whatever the process we have, that is P2 and P3, from that which is having the minimum number of execution time, that is burst time. So whether 3 or 8 means we used to say only the process P2. Okay, at the time 0, the only P1 is available. At time 0, the only P1 is available. So it starts and finishes at time 5. It is going to take only, it is going to take only 5 seconds. Okay. So at 0, only P1 is available. So it starts and finishes its execution time. The next one what we have, it is after all the time P5, all time P5, the P2 and P3 are available. P2 and P3 are available. The P2 has shorter burst time, so it starts at the time 5 and finishes at the time 8. See, so first one 3 when the input 5 is executed, P1 process, then the next shortest job is we have P2. So P2 will go and occupy the CPU, and it is going to take already 5 plus 3 8 milliseconds has to be waited by the other process. That is, the P3 has to wait until it completes the work. Then then it's similar to how it has been working is. At all time zero, only P1 is available. So it starts and earliest at time. It starts and earliest finishes time, which is going to occupy less number of time. Those processes will be allowed for an execution. That is we call it as an shortest job next. See the Gantt chart here. The Gantt chart. See that. So at a 0th millisecond, P1 will enters, and 5 milliseconds gets over. The P2 will take over the control, and after that P2, when it was executing 8 milliseconds, it will directly go for the other part of the program. That is other part of the program. So the P3 starts at the time 8 and finishes at the time 16. So totally, when you add all the first times of each process, you will be getting this same output, that is 11, 11 plus 5. 16 will be the total array execution time of the each process. Okay, is that clear? Right. Hope it will be clear. Okay. Then the next one is we'll see about the round robin. The round robin will be that each process is assigned a fixed timing slice or a quantum. The processes are executed in a cylindrical order. It is suitable for the time sharing systems and provides a good response times. The example, the process with a quantum time of 4, the process P1, P2, P3 arrives at 0, 1, 2 milliseconds, and burst time for each process is 538. So at the time of 0, the 4 quantum time is going to be allocated for the P1 process. So it executes 4 units, and remaining 1 unit has to be kept as in the ideal state. The very next time, when it reaches the 4 milliseconds, the P2 process is going to execute it. The quantum time for the P2 is also be the 4 time. Okay, that is the quantum time of the P2 is also 4. So, but it was actually required only 3. Anyhow, the memory is going to be given and it is going to occupy it, and it is going to give you the value as 1 back. Okay, the next one, and the P3 8 units is going to be allowed and it has to wait. The next thereafter, the time for that is the second cycle. Once it will go in a cyclic order, as we discussed that round robin is going to work, going to check the process within a round robin basis where you can have in a circular ring concept. So at the time of 4, the P2 process executes and the remaining 3 will be executing further. And then the time of 8, the PI executes for 1 minute of execution, and the P3 continues with the other remaining. Okay. Then the next one is at the time of 12, P3 executes for 4 units and remaining 4 units will be there. And at the time of again 16, if there is no other process to execute, then the same process will be allowed for the execution. The below is shows about the Gantt chart and the analysis what we have it in the right side. Okay. Then the next one is priority scheduling. Based on the higher priority, the processes are executed before the lower priority ones. Okay, for so what are the process? The same category C along with this information they are given an additional information, that is the priority. So you have the same process P1, P2, P3, but the priority of the process is been assigned with 2, 1, 3. So see, one is in a highest priority, 2 is in a higher priority, and the 3 is the lowest priority. Okay, see the P1 starts at the time 1, highest priority, and finishes at the time 4. Okay, and the next one, the P2 starts at time 4, highest next highest priority, and finishes at time 9. And the P3 starts at the time of 9 and finishes at the time of 17. So cat chart was shown below. The next one, the analysis also has been saying that the waiting time for the P1 should be 4 minus 0 equal to 0. The waiting time of the P2 could be 0. And the waiting time of the P3 is equal to 9 minus 2 is equal to 7. The next one is the average waiting time, that is, we'll be adding 4 plus 0 plus 7, 11 divided by 3. So we'll be getting 3.67 information will be the states. The next one is the summary of this is each scheduling algorithm has its advantage and trades-off. The FCF, that is the simplest, simple but can result in high waiting time. Then is SJN, that is smallest, shortest job node, minimize the average waiting time but can lead to starvation. The next one is round robin, provides a fairness and good response time but may lead to higher education process waiting time. Okay. The next one is the priority scheduling. Can we verify efficiently of its purposes are well managed but can also cause the starvation in the non-development. Okay, that is not handled it carefully. I hope you could understand the process management concepts. So we'll end up with this session. So thank you once again. Thank you all.